6.5, the logistic differential equation. So logistic growth begins as exponential function, increasing and concave up, and then continues concave down as it approaches what we call the carrying capacity. So this is a logistic growth function here. And what happens is they usually model growth of bacteria or animals or population or things like that. And so what usually happens is you'll start with a population of, say, 1,700. And then it grows quickly, but then eventually, because of natural phenomenon or food or disease or just old age, eventually the population will start dying off. And so this is what's called the carrying capacity. And so that's kind of like the maximum amount of people that are going to exist. So for example, if you lived in like a village, a small village, eventually say you can have 1-2 people and there's enough food. You have 10 people, there's still enough food. But maybe when you get to 100 people, there's just not enough food to go around. So in a larger scale, say there's 20,000 people in a city, that's the carrying capacity, because with natural resources, that's the most that people can be without running out of food or resources. So the idea here is that it will grow, and the parameter, the smaller k gets, the faster it grows. And then as you approach 0, it means it's going to grow slower. And this is the equation that we're going to talk about called the logistic equation, and we'll get into that. But the idea is that it grows, and this value here shows as time goes on how many people, and then it eventually will level off. So here's what a logistic equation kind of looks like, the general one. It's a curve that starts exponential. Really, you're not going to have anything on the left side of the y-axis. So realistically, you shouldn't have this piece here at all, because it usually starts at t equals 0. The inflection point is where it changes from concave up to concave down. That's when it's growing the fastest, because as soon as you get past here, the rate at which it grows starts to slow down. And then the carrying capacity is the horizontal asymptote that it'll never cross. So this is the differential equation for a logistic model. So you have dB dt equals k times p parenthesis m minus p, where p is the population, so it's the amount of people at that current time, and m is the max carrying capacity, so that's the largest the population can get, and k is the growth constant.